We're going to review what we talked about last time a little bit, and that is the voltage or the electric potential due to a point charge, which we already derived. But we'll rederive it, and then we'll talk about the voltage and the potential energy due to a single charge. And then we'll do the same thing for multiple charges. We have lots of different point charges out there. You know, what happens to voltage and potential energy. And then we're going to compare calculating voltage to calculating the electric field. And I should put a vector hat on there. Okay? So, anyway, just to repeat what we did before, if we have a point charge, just a little positive point charge here with a total charge of Q. Okay, we want to know what is the potential at some point. Now, it's really important for you to understand what we mean by what is the potential, electric potential, at this point in space. Okay, as a distance r away. And here's what it means. Look, if I put a little positive test charge right here, Q naught, and by the way, it doesn't matter what the magnitude of Q naught is because we divide it out anyway, but I had to do work to get that positive charge there, right? Because this positive charge, you know, it's got an electric field, and from infinitely far away, I had to take this positive test charge and push it against that field. And get it right there. And so really what electric potential is a measure of is how much energy per unit charge is stored up in the electric field because I placed that positive test charge there. Okay? Because look, if I let go of it, bing, it's going to fly away, right? And it'll gain kinetic energy and all that sort of thing. So that's what we mean when we say electric potentials. How much work per unit charge did I have to do to go from my reference position, which for point charges is infinitely far away, to that location in space? You know, how much work per unit charge did I have to do to get there? Then you just multiply by whatever this charge is to figure out how much work I did. Not work per unit charge, which is volts, but work, period. And what we did, of course, is we said that a change in voltage is equal to negative E dot ds. This is the definition of a change in voltage. And I said, well, this is a point charge right here, so the electric field due to a point charge is equal to negative kq over r squared in the, in the r hat direction, dotted with ds. And of course, r hat dot ds is, let's do this a little more formally. This is a dot product, right? So this, now it's the magnitude of this, which is just 1, times the magnitude of this, which is just ds, times the cosine of the angle between them. But ds cosine theta can really, really what we're doing is we're projecting, what this does is this projects our displacement onto the r hat direction, which means that this is really just equal to dr. So r hat dot ds turns into dr, which means that now my delta v is equal to negative, let's pull the kq out the integral of r to the negative 2 power times dr. And now remember what we did. We chose, well, we can just go r initial to r final from point A to point B. And when we evaluate this integral, we get delta v is equal to negative k. So you use the power rule on here, and you get 1 over r, that's r to the negative 1, but we need a negative in there, and we're going to evaluate it from r initial to r final. So this negative sign goes away, and we're left with, oh, I left the q out, didn't I? There we go. And so we have kq, and then what I'm going to do is just put 1 over r final minus 1 over r initial, like that. Now, here's something that we didn't really talk about. Notice that this change in potential only depends on my starting position and my final position away from the center of that. And that means if a change in this quantity only depends on where I begin and where I end, that means it's conservative. It doesn't matter what path I take between r initial and r final, I'm going to get the same change in potential. So that means that, hey, this electric field here, this force field, is actually a conservative field because of this result. Then we said, well, it's when I look at this, I go, hey, you know, it's pretty convenient to have a reference that will be the same no matter what your point charge is. And so if we let our reference position be infinitely far away, that is, we let r initial equal or be really super far away, well, 1 over a super far away number is 0, or approaches 0, or you're so far away that it's negligible. So we're just going to let that go to 0. And so we have the voltage rather than the change in voltage. We say the voltage is equal to kq over r. And really what this means is that, hey, this is how much work per unit charge you have to do to get this point charge here from infinitely far away. If I start infinitely far away and I push it against the electric field to get it here, then that's how much work I've done. Now, of course, to get the potential energy, U is just equal to that Q naught, my test charge, or whatever. This doesn't have to be a test charge. It can be any charge of this other particle that I pushed against the electric field due to this charge. And that's going to be Q naught times KQ over R. That is, I'm sorry, let me add a step in there. Remember that potential energy is equal to the charge that I moved times my voltage. And this is Q naught times KQ over R squared. And this becomes KQ naught Q over, not R squared, I'm sorry, over R. And I'm off camera, aren't I? Okay. Over R. Now, notice something very kind of cool about this equation. This is how much energy it takes to take two different point charges and put them together. Let's say you've got two positive charges and they're infinitely far away from each other, or super far away, and then I bring them together. How much work does it take to do that? Well, this equation really doesn't care which one's the test charge and which one's the original charge. It doesn't matter. So we can say that if I'm going to assemble a system of two charges, let's say I've got Q1 right here, and over here I've got Q2, and I put them a distance r away from each other. It took work to do that. Somebody had to do that. Somebody had to go and push them together because they don't want to be together. Well, how much work? I'm sorry, it's nothing personal. They don't have personalities. Okay, they don't dislike each other. It's just they repel each other. So the amount of energy it took to do that is just K Q1 Q2 over R. And it's really easy, and I do it too. I just did a few minutes ago, to accidentally put an r squared there because we're so used to having it 1 over r squared. But don't. This is potential energy. Now, does this look familiar? You might remember we had an equation similar to this for gravitation. It was G instead of K. It was the two masses instead of the charge, and it was still 1 over r. Of course, we had a negative out here, right? Because we had to, because they're attracted to each other rather than repelled. But anyway, this is the potential energy for, and this is the voltage. Let's see. This is for you, Seth. Here's the voltage for at a certain location from a point charge, and here's the potential energy to put 2 point charges, fairly close together. And remember, this is for 1 charge, and this is for 2 charges. This is joules per coulomb, and this is just for joules. You just have joules for units there. Okay, well, what if I have multiple charges? Well, if I've got like more than, let's say a whole bunch. Let's say I got 1. Let me just do this like 1, 2, 3, 4. And I don't know if these are positive or negative. It doesn't matter. Well, let's say I've got a point, and these are 4 point charges out in space, and I want to know what's the voltage right here. What's the voltage? Here's my little test charge. What's the voltage right here? Now, this, if you eliminate these 3 and just look at Q1, I have to do work against the electric field due to Q1 to get to that location in space. But then I also had to do work against Q2. And I also had to do work against Q3 and 4. So we just add them together. To get the total amount of work I had to do to move against the electric fields of all of these guys, I just have to add the voltages together. So I can say that the total voltage is equal to the sum, where I equals 1 to n, if I have n number of charges around here, of K Qi over Ri. Okay? So I'm just adding these up together. Now, we had an equation very similar to this for electric fields. Like if I wanted to know what is the electric field at this location in space compared to, what is the electric field at this location in space? And what I did was I said the electric field was equal to the sum of I equals 1 to n of K Qi over Ri squared, right? It's the electric field is inversely proportional to the square of the distance away. But then we had one other thing that we had on here that made this hard. Anybody remember what's missing from this? Yeah, R hat, or R hat I. It gets its own little index. Why is that? Well, because electric field is a vector. And so if you look at Q1, maybe Q1 is pushing it, way like this. Maybe Q2 is negative, so it's attracting like this. And Q4, maybe it's positive, so it repels, and maybe this is negative, so it attracts. But anyway, they each have their own individual r hat direction, and so each one of these contributors to the overall electric field, they're all in different directions. And so you had to add them together as vectors. Well, I don't know if you've noticed, but adding vectors is a big pain in the neck. But what do you notice about voltage? It's a scalar. There's no r hat here. There's no r hat. No, there's no. What are you talking about? Okay, no, you just add them. It's just KQ over R plus KQ over R plus KQ over R. And that's nice. That's really easy to deal with. So when physicists are trying to understand the field around a whole bunch of charges, what they really like to do is first look at, try to come up with a calculation for the potential around these charges. And then they can use that potential function to get the electric field later on. And that's what we're going to talk about next. But the nice thing about voltages is that, for point charges, or for anything, voltage is a scalar. So it's much easier to deal with than electric fields. Okay, so let me zoom out and we'll take a look at the whole thing here. Make sure I did everything. Why is this? Oh, I know. Okay, so make sure you understand how to find the voltage for a point charge. I'd like you to really understand this derivation using calculus. And then of course, this gives us the voltage for a single point charge. And then all you have to do is multiply by the charge to get voltage. To get energy. Multiply the charge times the voltage to get the potential energy. And then, of course, you've got the potential energy between 2 point charges. And then you can apply that to multiple charges to get the voltage. By the way, if you have a little Q naught right here, and you want to know, how much overall energy did it take to get that Q naught right there? Just multiply this sum by Q naught. And you've got it. Okay. Any questions? Clear as mud.
Wait, what did you just say? Say that again.
I don't remember.
So about Q naught and...
Yeah, say that again.
Well, okay, what you can do to get U is just Q naught times V, which is just Q naught times all of this. Oh, and by the way, remember, this is a sum, right? So what is the same in each sum? What can we factor out? The K, right? So, just when you're actually doing this in a problem, just, yeah, it's pretty easy. Okay.